which is Ekaterina Fokina, who will tell us about classification of effective structures.
Thank you. So my first question to the audience, to everyone who is here, should I wear a mask? Because I have a cough. It's not COVID, but I will probably cough during the talk. So if you want me to wear a mask, then I will do it. Or you may sit somewhere farther away.
Up to you, If I do get concerned, I'll get a mask.
Okay. 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 Wonderful. Thank you. So in this talk, I will. So I wanted to discuss two approaches to classification of effective structures. It won't be really anything new here compared to what I have talked previously, so I'm sorry for that, but I try to emphasize maybe some different things about the results and stress connections also to other areas of logic like descriptive set theory and so on. Okay, so the general question that we consider here, well, is the following. Suppose we have a nice class of countable structures, a nice meaning, well, closed under isomorphism, of course, and well, be not too complicated. And then the question is, how hard is it to classify effectively given structures from this class after equivalence relations? And by effectively given, well, I mean, mostly computable, but it doesn't really have to be just computable, meaning computably enumerable, things like this. Okay, and yeah, so I will discuss two approaches to this general problem that I have been working on, and yeah, so it's probably reasonable to start with just basic definitions, because during this conference there was not too much about computable structures, right? So throughout this talk, the languages will be finite, mostly relational, though in some examples there will be some functions, but it's doesn't really matter. And then we, as usually, identify formulas with the natural numbers through a good old numbering, and then we measure the complexity of a structure through the complexity of its atomic diagram. And then, well, the structure is computable if the atomic diagram is computable. It's computably enumerable if the diagram is computably enumerable. But for the case of finite languages, we can even simplify this and say that the structure is computable if the universe is computable, and we will mostly assume that it's all of these natural numbers. And the interpretations of symbols from L are computable. And similarly, computably enumerable, again, if the universe is computable and the interpretations are computably enumerable, even though, yeah, yeah, now that I realize I will not really be talking much about computably enumerable, but anyways. Okay, and then we can effectively enumerate all the atomic diagrams of computable structures. Just pick your favorite way, just as the indices of atomic diagrams in the enumeration of computably enumerable sets, or just take specific universal enumeration of computable structures for a fixed language, which also exists, right? So whatever you prefer. And then we measure the complexity of relations or on classes of structures, of some properties on classes of structures, by the complexity of the corresponding sets of indices, yeah, in this enumeration. And this is the first approach that I'm going to talk about. This is the approach introduced by, well, The framework for this approach was introduced by Goncharov and Knight. And so they said, let K be a class of countable structures closed under isomorphism, and let us consider the set of all computable structures from K. And well, we identify structures with their indices. Then the class itself, the computable members of the class may be identified with a set of indices, this index set for structures from the class K. And by saying nice, when I said that we want the class to be nice, we mean that this index set is hyperarithmetical, so the class itself is not too complicated. Right? And by the result of Goncharov and Knight, it means that, well, it's equivalent to saying that the class K is the set of models of some computable infinitary sentence. Okay, so these are classes that we consider. So we do not want the complexity of the relation on classes of structures to come from the complexity of the class itself. And for this reason, we restrict, we adopt this restriction. Okay, and then we can do the same trick for binary relations. Suppose E is a binary relation, and on the class K, then this relation computable members of this class can be identified with the set of pairs of indices of structures from K that are E in the relation E. Yeah, so think of E, well, it's usually isomorphism, but maybe also some other equivalence relation, or not even an equivalence relation, maybe some kind of ordering or something. Okay, and then what Goncharov and Knight suggested to measure the complexity of such binary relations through the complexity of these index sets. So to see where these sets lie in the hierarchy of sets, like and characterized in terms of M completeness at some level. Okay, so using this approach, basically classifiable class is classifiable. If it has a classification, means that there exists some hyperarithmetical. So that this set is hyperarithmetical. Okay, so it means that it well, if E is, let's say, isomorphism, right? Then we and the class itself is hyperarithmetical. Then to say that okay, two structures are isomorphic means that we need to say there exists an isomorphism. And so in the worst case, it's sigma 1, 1. So to have a classification means that we have some simpler means to classify the structures, to find some invariance, right? So being hyperarithmetical in this situation means a good situation means having a classification. Okay. And this approach has been used quite a lot, and there are a lot of results. And here I list some of them for some classes. And it has been studied mostly for isomorphism. So this notation means the set of indices for isomorphic copies of K. And so for vector spaces, algebraically closed fields of fixed characteristic for torsion-free abelian groups of fixed finite rank. This the isomorphism problem is M complete among sigma 03 sets. For equivalent structures, it's pi 04. for this structure. This is a good situation. So these classes have some invariance, right? And it also corresponds to our intuition. And then for other classes, the this set of pairs of indices of isomorphic structures is as complicated as it's possible at all, right? For graphs, abelian P groups, linear orderings, Boolean algebras, and so on and so forth. Everything that's listed here. Okay, so all of these results characterize these as M-complete sets of some particular at some particular level hyperarithmetical analytic hierarchy. Okay, and when I came to Vienna, we modified this approach a bit with the motivation coming from two different sides. So we started this with Cy Friedman, so my motivation and his motivation, like combined into modification of this approach. And let me talk about it a little bit. So one piece of motivation comes from the theory of numbering and the theory of well, equivalence relations, as it's now known probably better. This is a definition given by Yershov, formulated in more modern terms, maybe. Suppose we have two equivalence relations, and then we say that E is computably reducible to F. If the two equivalence relations on omega, if they E is computably reducible to F if there exists a computable function such that E equivalence can be reduced using this function to F equivalence. So very natural definition. And in the last 10-15 years, there has been a lot of work in this area. And some of the papers listed here, but also many more by now. So about the structure of equivalence relations on the natural numbers under this computable reducibility. And well, the second piece of motivation comes from descriptive set theory, from Borel reducibility. So it's basically the same definition, well, similar definition for equivalence relations on Polish spaces, and the reducing function has to be Borel. Okay, and then we combined with Cy Friedman, we combined this all together, like all these three pieces together: the Goncharov-Knight's approach, the computable reducibility, Borel reducibility, into this notion here. So what do? We consider, again, a nice class of structures, meaning that the index set of computable structures from this class has to be hyperarithmetical. And we do the same as before. We identify a relation with the set of pairs of indices of structures from the class K that are E equivalent. But now we consider this as not as a set, but as a binary relation on the natural numbers, or on a subset of the natural numbers, right, on I of K. And then we say that E, such a relation E is should also computable, probably reducible to f if there exists now a partial computable function, which is for sure defined on x, and the range of x, the image of x is inside of y. And well, oops, the reduction is still the same. Yeah, the question about E equivalence can be reduced to the question about F equivalence. Okay, by this partial computable function. Yeah, so this is the only difference compared to the computable reducibility for equivalence relations on omega. Okay, and then we studied this this relation this reducibility for various equivalence relations on computable structures. The first one that we looked at was bi-embeddability, and we showed that bi-embeddability on computable graphs and on well, other standard classes will be sigma 1 complete among equivalence relations using this computable reducibility from the previous slide. Okay, and this result was not actually surprising. It was just effectivization, like in a sense, of the corresponding result from descriptive set theory by Lovo and Rosenthal. They prove the same for countable structures and equivalence relations on counter space using Borel reducibility. Okay, what was more interesting was this result, well, the same result about sigma 1 completeness of isomorphisms on computable structures. So for computable structures, the isomorphism is sigma 1 complete among all sigma 1 equivalence relations on omega, using this notion of reducibility. It's different from the descriptive set theoretic case. Well, because, well, first of all, isomorphism on any class is known to be not complete for sigma 1 equivalence relations. But even if we consider only even if we restrict our attention to only isomorphisms on countable structures from some classes, for example, abelian P groups are not at all complete in this sense. Okay. So this is something that is this result is something that is different from descriptive set theory. Okay, and then also we considered with Cy Friedman and Andreanis, we considered computable isomorphism, the relation of computable isomorphism, and we showed that it is sigma 0,3 complete. Well, it's yeah, so it's sigma 0,3 complete among equivalence relations using this notion of reducibility. And then we could also lift this result to arbitrary computable successor ordinals. And the final point here was the result by Greenberg and Turetsky, who showed that the relation of hyperarithmetical isomorphism is complete for pi1 equivalence relation. Okay, so I didn't put a year here. The result has been here for quite a long, but the last time I checked, I think it's still not published. So I don't know what it was, 2014, I think is when I learned about this result. Okay, and then for completeness, I want to mention this n reductions as some kind of refinement from m reducibility to the computable reducibility. So an n-ary computable reduction of a relation E to F consists of n computable functions such that for every n tuple x1 to xn, we have that xj is E equivalent to xk if we have this relation here. Yeah? So here E and F are just relations again on the natural numbers. Yeah? So this is a general definition for relations on the natural numbers. And well, they form some kind of hierarchy. As I said, well, if we take n equals 2, we get m reducibility, and then they go higher and higher and higher up. And if we introduce countable reducibility, then it will correspond to computable reducibility as defined before. So countable reducibility basically says we have a computable function such that for every countable list of elements of omega, the function outputs another list of elements such that the same relation holds. And so this is exactly computable reducibility. What is interesting here that all of this can be also transferred into applied not to computable structures but to countable structures, and the picture there is quite interesting. For example, and these are results by Knight and Russell Miller. They studied these countable reductions. Well, they formalized these countable reductions also for the case of countable structures, for the case of relations on Cantor space, and in particular for classes of countable structures. And they studied, for example, countable torsion-free abelian groups of some fixed rank R, and they proved. Let me point. They proved this very interesting result that torsion-free abelian groups of rank 0 lie strictly below torsion-free abelian groups of any higher rank, and all of those form one class up to this countable reducibility, which is, of course, a very different picture from the case of Borel reducibility. Yeah. And so it would be nice to see more results like this, and more results about this finite reducibility applied to classes of countable or computable structures. So there are some results that show that this hierarchy is strict, right? But this is all about just relations on omega. This is not about relations on classes of structures. It would be nice to see if we can say something using this reducibility also for structures, or for classes of structures. Okay, so let me finish this talking about this approach, and let me start with another one. Yeah, this is something that I have been working on and talking about in the recent time. So And the setting is the following. Suppose we have a class of countable structures, and suppose that we are observing one of those structures stage by stage, growing finite pieces of the structure. And the task is, after finitely many steps, to say, okay, this is the structure we are observing. So after finitely many steps, we need to assign some kind of identifier to our structure, saying what exactly we are seeing. So, and I call it on-the-fly classification for this reason, because by seeing this finitely much of the structure, we need to be able to put it into a correct box. Yeah, so in this situation, a classifiable class is classifiable if after finitely many steps we can correctly assign the name of the box or index for the structure we observe. Okay, and yes, and well, this is the situation very different from before. Well, because even it might happen that we have just two, well, finitely many structures, for example, just two of them, and we cannot do this trick. As in some situations we can, in some situations we cannot. Now, for example, if we have these two linear orders, the naturals and the negative integers, then we can, of course, after finitely many steps, output a correct hypothesis. So we say, well, we just start looking at what we are receiving, and as long as the new elements appear, let's say, to the right, we output the hypothesis omega. And if a new element appears to the left, then we change our mind. Sorry. Well, if something in between appears, we do not really care. And then again, if something new appears to the right, then we change to omega, and so on and so forth. And then from some point on, we will see the real zero. Yeah, it will appear. So from that point on, all the new elements will start appearing, let's say, to the right, as in this situation. So our hypothesis from this point on will be omega, and it will stay omega forever. So it's all fine. If we consider a similar situation with the natural numbers and all of the integers, then we cannot do this because we can, well, we will be infinitely often alternating between hypothesis for omega and for the integers. And this is not what we want. Yeah? We want, after finitely many steps, to output either one or the other. Okay. And well, the questions that, well, one needs to solve here. Well, first of all, what we mean by revealing finite pieces of the structure. And well, mostly till now, we consider the case when we see both the positive and the negative information about the structure as motivated by computable structures, right? So we see those finite pieces, and we know how the elements are related, those elements that appear, how they are related and how they are not related. We also considered slightly the case motivated by computably enumerable structures, where we only see the positive information, right? So we know if the elements are related, then we know that, but they are also allowed to become related at later stages. Okay. And yeah, we need to say what we mean by classifying or identifying structures. And it turns out that it's convenient to use the terminology and ideas from algorithmic learning theory. However, I still think that these results are more results about computable structure theory. Yeah? So they belong more to computable structure theory than to learning theory. They reveal interesting links also to descriptive set theory and topology. Some I will mention, others I'm not ready to talk about, but hopefully in one of the next talks, or maybe one of my co-authors, we'll talk about more results motivated by all this framework and more and all this this approach. Okay, so but still, learning theory terminology and methods are already there, so we use them. Okay, most of those, most of the results in this field are about learning of languages or functions, so pretty much unstructured information. And what we want to do is to apply this to study learning of computable, learning of structures. Yeah, they do not have to be computable, those structures, and we'll talk about it in a minute. So we were not the first to do this. There is a sequence of papers, not too many, but still quite some, right? That studied learnability of classes of structures. And okay, and yes, so yeah, so in the most general case, what we want to what we want to do, we want to learn the isomorphism type of a given structure. Okay, so we want to learn. First of all, we need to be able to name such an isomorphism type, and that's why we focus here on learning of copies of computable or computably enumerable structures, or classes, some kind of classes of structures that can be numbered by the natural numbers, even though later I will talk about how to maybe extend all this framework to also to uncountable classes of structures. Should be possible to do, as you will see. Okay, on the other hand, the learning should be independent on the way how the data arrives to us. So for a successful learning procedure, we require that it should work for all isomorphic copies of a given structure. So the structure that we are receiving, it doesn't have to be computable itself. Okay, so this is the slide with the main definitions, again from the learning theory, given on an example of graphs for simplicity. Well, we have a family of graphs, and each graph GI contains infinitely many I+1 cycles. So it's pretty obvious what kind of procedure we want to have here. So we just wait for a cycle to appear, and then when we know what cycle it is, then we know what structure we are looking at, and so we output the corresponding index. How can I output the corresponding name for our hypothesis? So it's a pretty simple example here. So the point of this example is just to introduce the definitions. The learning domain is the family of all presentations of the graphs. This is what I was talking about on the previous slide, right? All the isomorphic copies of those graphs. And we receive both the positive and the negative information about any given such graph. So if two elements are related, we know that at the stage when they appear, and if they are not related, then they will stay not related. So we know it at the moment when both of them appear. Okay, this is in the terminology of learning theory, it's called learning from informant. And well, as our hypothesis, we output, as our conjectures, we output just the natural numbers or the question mark, meaning that we still do not know what exactly we are looking at. And I will talk about this hypothesis space in a second, or in a minute. Okay, then the learner is simply a function that up to isomorphism learns any graph, any isomorphic copy of this graph. So in general, we do not measure the complexity of this function. So it's a function that gets as input this finite substructures, let's say, or finite atomic diagrams that grow and outputs a hypothesis. Okay, so this is the learner, and in general, we do not measure the complexity of this function, but we might if we want to. Depends on the task that we have. Okay, and then we from the beginning assume that these are the only structures that we observe, so we do not care if we get as input some other structures. Yeah, so we think that we do not get anything else but such graphs. And we say that we successfully learn this class if eventually, after finitely many steps, we stabilize to one and the same correct guess about the graph. So we start with putting one and the same correct hypothesis. Okay, and this hypothesis, this is the only technical issue here that still needs to be discussed. How exactly we interpret those conjectures. Okay, and this is, let me see. Yeah, so this is something that I will probably skip now. So let me just mention there are two possible approaches that we considered here, and both of them have their advantages and disadvantages. But basically, one of these approaches is good when we do not care about the complexity of the learner, or maybe we do not care how the complexity of the learner depends on the complexity of the class of structures that we consider. And the second approach is more precise and is used when we also want to see how the complexity of the learner depends, among other things, on the complexity of the class itself that we are learning. Okay. So anyways, by specifying all these parameters, we get this notion of learnability, and in the tradition of learning theory, it gets this kind of index, a prefix here at the beginning. But okay, as soon as we fixed how exactly we learn, we get both the positive and the negative information. We learn, we want to identify structures up to isomorphism. We want to, well, as our criterion of success, we have that we converge to one and the same hypothesis after finitely many steps. So we can forget about this about this prefix. Okay, and this is what we will do. So from now on, I will just say learnable, using these definitions, and I will come back to variations of all of these parameters in a couple of slides. Yeah, so with Lucas and Mauro and Nikolai Bazhenov, we were able to characterize which families of structures are learnable in this situation. Well, we gave a syntactic characterization of this notion of learnability. And well, using just infinitary, computable infinitary formulas. Computable infinitary formulas, I put the definitions here, but I think I will skip them. Okay, so the important thing here is that being learnable in this case means simply that we have a sequence of sigma-2 sentences that uniquely describe structures inside of this inside of the class. Each structure is uniquely characterized by such sigma-2 sentence. Okay, and then we can effectivize this if you want to measure the complexity of the learner and do everything effectively. And basically what this corollary says that the complexity of the learner in this situation only depends on the complexity of the oracle that we use in this sigma-2 computable sentences that describe the structures from the class, plus the complexity of the class itself. Yeah. Yeah. So the complexity of the enumeration of the class, roughly speaking. Yeah. So this is something that I omit with this second approach, right? So if we are interested in how the complexity of the learner depends also on the complexity of the class, then we can measure that. You know? So we can tell that using this corollary that we got. Okay, and this is a kind of well, it depends on how one interprets this, but I think that this is a nice result. Just because having a syntactic characterization of some kind of property usually, well, means like some kind of robustness of the notion, right? So this is a nice notion that can be described syntactically. Okay, and then we use this to get examples of learnable and not learnable classes for various natural kinds of structures like lattices, abelian groups, linear orders. And we show that this is impossible, for example, for Boolean algebras. Okay. And then this is I think something interesting by Bazhenov, Cipriani, and Mauro. They showed a link of learnability in this setting to a descriptive set theory as follows. They showed that a family of structures is learnable if and only if there exists a continuous function, well, which basically reduces the isomorphism on structures from K to the relation E0, not with eventual equality. And well, and once we have this, now we can, if we take this as simply a definition of being learnable, right? We can extend this also to maybe from the very beginning, uncountable classes of structures and things. Yeah, to generalize all this approach further. Yeah, so now we, yeah. So this is something for the future. Okay. And what else one can do is one can also generalize this notion of learnability by plugging in an arbitrary equivalence relation E here. Now, instead of E0, taking some kind of E, and we say that a family of structures is E learnable if there exists a continuous function that reduces the isomorphism to this relation E. Okay, and then they showed several interesting results that, well, for the typical benchmark equivalence relations studied in descriptive set theory, they showed that this for E0, E1, and E2 relations, the notions of learnability coincide. For E3, the situation is different, still coincides when we talk about finite families, but it is different for infinite families. And then they could also find a syntactic characterization of E3 learnability. And well, they also did some other interesting things there. They, for example, defined the notion of reducibility here related to learning. We say that the relation E is reducible to relation F, like learning reducible to relation F, if everything E-learnable, like every E-learnable class is also F-learnable. And they got some they put almost all of these benchmark relations in a diagram, which of them reduces to which one. And the situation, modular one open question, looks surprisingly similar to the case of countable reducibility, which I mentioned by Russell, Miller, and co-authors. And yeah, so the question is if it's just a coincidence or maybe there is some deeper reason for that. Yeah, it's probably a coincidence, but maybe it's not. Okay. Okay, so I'm pretty much done. So this is something that I said I would discuss. So if we modify those parameters of learning, we can get new notions, and many of them also natural and absolutely worth of studying. For example, if we change the information source, if we may think that the structure that the information about the structure that we are receiving is not both the positive and the negative, but only the positive information, right? In learning theoretic terms, it's called learning from text, right? So it's motivated by like CE structures, right? So we see when the elements are related, but maybe they will, now they are unrelated, but they will become related at a later stage. Or maybe we get information about the structure in some kind of delta 0-2 way, right? Related, not related, related, and so on. It's also something to consider. We may learn up to some other equivalence relation, right? So we may say that we have to output an index of a structure that is not necessarily isomorphic to our structure, but maybe just approximately similar, right? Bi-embeddable. Or maybe we want to say, to make it stricter, like the other way around, to make it stricter, to output an index of a structure that is computably isomorphic to our structure. Or maybe mix it together, they relax it structurally, but make it more precise algorithmically, and consider this computably bi-embeddable, so on and so forth. Maybe some other relations also to consider here. We may change the convergence behavior. So instead of saying that after finitely many steps, we have to start outputting one and the same index, we may relax it to BC convergence, which means like outputting eventually starting outputting we have to eventually start to output indices for a correct structure, but those indices may be different, or maybe the other way around. We want to be very strict, and we say that we can wait for a while, but as soon as we output a hypothesis, it should be a correct one. Okay, so things like this. Yeah, so all of those being natural things to consider. Yeah, we may also ask what classes are learnable by learners of such and such complexity and things like this. And there has also been some research in this direction already by Mauro and Bazhenov, and maybe someone else I forgot already. Okay, so this is just to show you that we did study some of those questions. For example, this studying like learning up to different equivalence relations on the case for equivalence structures. We know that learning equivalence structures up to isomorphism is different than learning from up to bi-embeddability, and the same for computable versions. And also we started studying the learnability from text, right? From only the positive information. And here I would like to be more cautious than I previously was. So it's still work in progress. And so the goal here is to get a similar kind of syntactic characterization of this notion of learnability. And we introduced also some, well, not introduced, that's we used positive infinitary formulas defined by Soskov here. And the goal here is to show that this kind of learnability corresponds to the property of being characterized by sigma 2 positive sentences, similar to how we did for computable infinitary formulas, like for usual infinitary formulas and learning from informant. So we are confident that we can do it in one direction. So if we have such sentences, then it's TxtEx-learnable. So the reverse, so I still formulate it as a conjecture, but so we are working on it. So hopefully, yeah, we can also characterize this notion of learnability here. Okay, this is my last slide. So thank you.
Thank you. Are there any questions?
So as far as I understood, the characterization between learnability and this learnability up to E0, yeah. It's for the having both positive and negative information, right?
Yes.
And are you also considering the direction of finding something similar with this? I mean, apart for the syntactic characterization, also for, I mean, some equivalence relation that could give the learning up to only positive information.
Yeah, that would be nice. It would be something different from E0. It would be some relation, probably even, yeah, because we want to get something like this, but it will be something different because also the topology that corresponds to learning from text is a different topology. It's more like a Scott topology. This is what I said, that these are results that I'm not yet ready to completely discuss here. And so this is also some kind of work in progress. Yeah, so hopefully something will come up there.
Thank you.
There's in computable structure theory, there's a difference between looking at computable categoricity and looking at relatively computable categoricity. In the syntactic description is in the relativized case.
Yeah.
And things can be quite different if you just restrict to only computable objects. Do you see any instances of that kind of extreme dichotomy in these investigations?
No, not.
Because your learning thing is sort of like the relativized case, right? Because
Yes.
you allow any presentation of
Yes.
of the structure.
Yes. So, well, we define it like this, that we want to learn, from an arbitrary structure. We didn't really consider just learning only the computable copies of a structure. Yeah. Maybe we should, yeah. Probably we should, yeah.
Any other questions? So we can look online. All right, so let's thank Katya again.
Thank you.
Our next talk will be at 2:30 with Giovanni Solda.